Okay, this is problem sheet 5, and I'll go through the model answers for you. So looking at the first question is this difference equation is given to you, and also the second one is given as well. You have been asked to show that both filters have same magnitude response. The magnitude response of this and this one has to be same. So we do one at a time. We start with the first one. So we write the equation, and then it takes a transform, YZ, you know how to do that, Ci xz z to the minus I, and then you find the transfer function yz over xz, which is h1z, which is Ci z minus I. Then you substitute h1 theta, so h1 theta, that's the magnitude, which is sigma I equal to minus m2 plus m Ci e to the power of minus j theta I. And if you take the modulus value of that, and that will be the modulus. That's for the first one. And the second one, then start with the second equation. That's the equation second one is. And you take this transform, same format. We could just omit the step, go straight to that. From there, go for that step. So which is yz over xz will end up as Ci z minus m z minus I. So what we need to do is now h2z is here. This is h2z. Now we need to find h from here. We need to find h2 theta. So which is easy enough. You can just substitute here sigma Ci will be there, and e to the power minus j theta m times e to the power minus j theta I. So we take the modulus of that, this modulus part, that means the modulus of that much, and we separate the modulus into two separate modulus, and e to the power of minus j theta m, and if you take the modulus, that's v1, because that's cos theta m plus j sine theta m, and the modulus of that is square root of cos squared plus sine squared, which is 1, therefore that's equal to 1. So this is 1, therefore you end up with h2 is that one, h1 is this one, and they're exactly same. So modulus h1 theta is equal to h2 theta. So it's just it's not a difficult question. You just need to go through the step by step there. Let's look at the next question. They want you to compute 3 dB bandwidth of one transfer function here and two transfer function. We start with the first one. h1 set is given to you, and now you find h1 theta, which is 1 minus a over 1 minus a e to the j theta. Now we learned few methods of finding h1. You can find h1 theta modulus squared by multiplying h1 theta by its conjugate h1 theta, and if you do that, you will get here is 1 minus a over 1 minus a e to the minus j theta times 1 minus a divided by 1 minus a e to the plus j theta. That will be the conjugate, and if you multiply them out, that's what you do, you will get 1 minus a squared on the top, and then this one is, you know, if you multiply this out, you will find this is your answer. This is done using just modulus method, this one is, and if you use this conjugate method, you know, they both give the same answer. So now we know that the modulus value, that the power modulus squared is equal to that. Now 3 dB bandwidth, remember we learned that whether it's a low pass or high pass. If you take the low pass filter, this is 0 dB, minus 3 dB is here, minus 3 dB. So the bandwidth means that frequency, theta c, that's what we are trying to calculate. And if you assume this is 1, and this would be 1 over root 2, down. So one or the other you can do. So that's in voltage. If you take in power, this will be 1 and this is 2, half. So this is power, this is voltage, this is whether power or this is in dV. So both all are same. In our case this is squared, so we just take the power part. So we are trying to find out theta c, that's a cutoff frequency, when theta equal theta c is equal to half. So when this is half, that point, what is that one is we are trying to find. So all you need to do is that half is equal to, you substitute 1 minus a whole squared divided by 1 plus a squared minus 2a cos theta c1, and now you do cross multiplication and here and find the value cos theta 1, that gives you that answer. So that's just simple algebra. So we have calculated the cutoff frequency, cosine of the cutoff frequency theta c1. So if you really want theta c1, because theta c1 is equal to cos inverse of that one. Now similarly we take the second transfer function, which is here. So this is the first one answer. Second one is this your transfer function given. So you find h2 theta. And then whichever method you use, you can find h2 theta squared, which works out to be this one. Now the same principle, same as we did. That's the filter. Now half power point. What's theta c2? We're trying to find. So you calculate theta c2. So when this is half, you substitute instead of theta c2. So you get that equation to be solved. Cross multiply this one and this one, simplify for theta c2, cos theta c2 will become that. Or theta c2 will be equal to cos inverse 2a over 1 plus a squared. So that's that one cutoff frequency. The second cutoff frequency theta c1, the first one. The first one is 4a minus a squared minus 1 over 2a. So that's the answer really, cutoff frequency for both filters. Then you are asked, which is, if you go back to the question, which filter has a smaller cutoff bandwidth? That's what the question is. So you can look at here, cos theta c2 is greater than cos theta c1. By looking at this fraction and this one, you can say that cos theta c2 is going to be greater than cos theta c1. Therefore, theta c2 must be less than theta c1. So if you have your cutoff frequencies, if you assume both are filters, so one is one low pass filter like that, half, that's 1 and 1 over 2 half power points. One is that one, which is theta c1. And the second one then is again a low pass filter, probably something like that. It could go do something like that. And at the same point, that would be theta c2. So the value A determines, in both cases, so for the same value of A, and one is theta c1 is greater than theta c2. Okay, you can, if you're not sure, if you are unable to work it out, you just put A equal to half and use your calculator to figure out. That's the easy way of doing it, if you can't figure it out from this fraction. Okay. All right, then move on to the next question. Find the magnitude response of this system. That's this question is. So you should normally rewrite this should be equal to z to the minus 2 plus 3 over 1 plus 3 z to the minus 2. Yeah? Or the other way around. So it should be like this, right? 3 plus z to the minus 2 over 1 plus 3 z to the minus 2. Now we learned yesterday these coefficients are roughly same, so in that case it will look like all pass filters, but we'll prove that. So we wrote the thing here and we substitute h theta is already substituted this way without transferring into this. You've directly substituted, which is possible. This is one way of doing it. And then you find mod h theta squared, and which worked out to be 1. Or you do it this way. Remember, h z is equal to 3 plus z minus 2 over 1 plus 3 z minus 2. H theta is equal to 3 plus e to the minus j 2 theta divided by 1 plus 3 e to the power minus j 2 theta. Then say H conjugate theta is equal to 3 plus e to the j 2 theta over 1 plus 3 e to the j 2 theta. And then you multiply mod H theta whole squared will give you H theta multiplied by H complex theta. Then you multiply these two very easily and you will end up with the answer 1. So it's an all pass filter. Then simply knows it's an all pass filter. Modulus is 1, so it's an all pass filter. Now you want to do a canonic realization, so you must have it in terms of delays. So we wrote that transfer function there. So we get it here. And once we have got that, you draw canonic function. This is 3 plus z minus 2. So there's 1 going 3 directly. And z minus 2 times no coefficient is 1. So z minus 1, z minus 2, that's coefficient is 1. That's yn. Then if you look at the feedback, you got, there's nothing on z1, because there's no z1 here. Only 3 z minus 2, so it will be minus 3 and z minus 2, z minus 1, z minus 2. And they add them up. That becomes your canonic realization. Where in canonic realization, you minimize the number of delays. So you will have the feedback path in the front, feed forward in the back. So that's another straightforward question, similar to what I've given in your lecture notes. Now here's another one which you ask you to find the H theta, not modulus, just H theta only. It's a lattice filter. It's a new type of filter you haven't come across, but the structure is similar. Structure is easy to follow. So the xn goes in here, and the yn is here, and also you can feed output here as well. So this question, how do we do that? So first we write the equation for yn. That's the first equation. Yn is equal to, that's yn is equal to wn coming in plus yn minus 1 multiplied by minus b. So wn plus yn minus 1. That's the first one. Then Vn, we'll write something for this one. This is equal to yn minus 1 coming through here plus yn b multiplied by b. So yn minus plus byn. And the third one is wn. So how do you find wn? Wn is here, so xn coming in, vn minus 1 is here, multiplied by minus a is added to the xn, you get wn. So wn is equal to xn minus a vn minus 1. So what we need to do from here is basically, we need to remove vn and wn from the equation so that you can relate yn and xn. So yn is equal to xn minus a vn minus 1. Yn is equal to wn. So it's used with the first equation. So what you need to do is for wn, you substitute this one. So that's what I have done. And the minus is still there. So that's the first part of it. Then you substitute for vn minus 1. You can substitute here vn minus 1. So what do you get? Vn is there. So vn minus 1 will give you yn minus 2 plus byn minus 1. And put that in here for vn minus 1. Put that in here. So that's that. And that's there. Now you simplify this one. Combine them all together. You will find this equation from that equation. Now if you take the Z transform, all these will come to this side, this side. So you get yz over xz equal to 1 over. This one will come this side. So b plus a z minus 1. This is z minus 2. Bring it to the other side is plus. So that's that. So h theta is just simply substitute z equal to e to the j theta you get. You're not asked to find the magnitude response. It's only a frequency response. So if you try to do magnitude, it will take a long time there. So just to be careful of that. Read the question very clearly. Is frequency response mean h theta? And if you are asked magnitude response, then only you're going to find that. So read before you start with the question, read it carefully, right? What you're trying to do. Now here's the structure given, and you asked to show that there's a linear phase characteristics. So you can see simply from the structure you're going to show, but you can always do it many ways you can do, but you should know this is a linear phase because it has got coefficients of that and is symmetry around that. These two are equal, so it's a linear phase filter, but we must show this. You've been asked to say show that it's a linear phase filter. So you write the difference equation, xn minus 1, xn minus 2, xn minus 3, xn minus 4, all added up, get yn. That's the one. So if you do the set transform, h set equal to this is like a power series, 1 plus r squared plus r n minus 1 is equal to 1 minus r to the n over 1 minus r. That's from your table of power series. That's on your data sheet, it will be provided to you. So what you find now is, if you apply this one, you'll get 1 minus r to the n should be equal to 5. You can see if it's n minus 1, you get n there, 1 extra. So this will become set to the minus 5, and this also set to the minus 5. Instead of that, I've just done everything in n and then substitute n equal to 5 here. But you can start straight away here. You can say 1 minus e to the j theta 5 over 1 minus e to the j theta. You can do that way as well, okay? Or you substitute n equal to 5. So once you have this, some people find it difficult with n, so you can just have this one. Then the next thing would be, you can see it here, you must take out half of this outside. So this should be equal to e to the power minus j, sorry. Let me rub it up. So you can say e to the power of minus j 5 theta over 2, you're going to take out. When you do that, you get e to the power of j 5 theta over 2 minus e to the sorry, there's a minus sign missing. This was also one, right? Minus. So e to the power of minus j 5 theta over 2. Similarly, here you can say e to the power minus j theta over 2 you're taking. So e to the power j theta over 2 minus e to the power minus j theta over 2. And from that, that's exactly in terms of n. So you have taken out, and you get this two terminology. Now what you need to do is divide this by 2j and divide that by 2j. And when you do that, this will give you sine. This also will give you sine. So that will be the thing. And you bring this up here, it will give you e to the power minus j 5 theta over 2 times e to the power j theta over 2, right? And so if you do that, it will end up as this is equal to e to the power minus j 2 theta. And this will become sine 5 theta over 2 here. From here, if you come from here to here, sine 5 theta over 2. If you come from here to here, sine theta over 2. If you come, this one is equal to, so this whole thing is equal to that. If you come from there to there, you get that. Now you can say that this is the magnitude part, like contribution magnitude part. This is only for the phase. So you can say from here, phase is that this part, right? So 5 theta equal to minus 2 theta, which is a linear phase. So you need to manipulate the equation. So it's not difficult, straightforward. Write the equation and then just do simplification. Okay? Next question. Now, this question, you have been given a causal IR filter. Is H stat a stable function? First the question. Now, stability is controlled by poles, right? Poles must be inside the unit circle. So if we look at poles, we are going to look at the poles. So that's your. We don't need to worry about zeros. And this is set equal to 3. So this is modulus set equal to 1. So set equal to 3 is here. So you have a pole at 3. So the system is unstable immediately. And this one, if you simplify them, the poles are going to be complex, but they will be inside. If you use the quadratic formula and find the poles for that, right? So if it's not stable, so we know it's outside, it's not stable, find a stable transfer function g set such that g theta and h theta are same. So we must find another transfer function which makes the system stable, but the magnitude response are same. So how do we do that? So what you need to do is, remember we did this all-pass filter? So we need to have that thinking. So we must find a way to have a zero here to cancel that pole. In all-pass filter it says, if you have a zero outside, you need to have a reciprocal of that. So you must have a zero inside 1/3. This is 1. If this is 3, you should have a 0 at 1/3. So if you have a transfer function which has got a 0 at 3, 0 at 1/3, and 0 at 3 and pole at 1/3. That's what the all-pass filter is. Then what happens is, then their magnitude response is the same. So what we need to do is, we start with our function, which is h set, which is equal to 2 z cubed. We don't need to worry about this at all. This does not contribute to any stability at all. 9 divided by z minus 3 times z squared plus z plus 0.5. We need a all-pass filter which cancel this out. At the same time, it is a stable filter. So we put in z minus 3 here, that is a 0, over 1 minus 3z, that's the pole. You know this one is an all-pass filter. Right? You can just take that separately and do it. All-pass filter, remember? All-pass filter we learned in the class, where if you have a pole inside, to make it all-pass, if this is R, you must put a 0, reflect this one at 1 over R, and you can put a 0 there. As soon as you do that, the characteristic become all-pass. The magnitude is an all-pass, yeah? So here, the same principle I've done. So to make this stable, I need to find another transfer function and multiply. So my new transfer function G set is going to be this one multiplied by this one. That's my new one. So in that case, what happened is, as I said to you, these two cancel out. So you will find here now, this fellow cancel out with that fellow as soon as you multiply with that. So you will get a new transfer function which is called G set, which is the original that will be there, and these two cancelled out. This will be there, and plus you have got another term. Where is it? 1 minus 3 set. So which we call G set is H set times of A set. This is an all-pass filter, and when you do that, that's given here, look. And the magnitude response of that, and the magnitude response of this one and this one, this is 1, so this and this are exactly same. But system is stable. So it's just a clever way of doing it. But this is where the all-pass filter thinking comes into play. It can be used to cancel out a pole which is outside the unit circle. So the overall system will be stable. At the same time, they have same magnitude response. Think about it again. Now we come to a two-pole low-pass filter, which has a system transfer function given there, and they want you to find the value of K0 and B1 such that frequency response H theta satisfies this condition. That is a DC gain. That is 3 dB cutoff. So first we write the equation, and then find H theta and substitute theta equals 0. You can do that. Or if you want to find the DC gain, so H theta and then theta equals 0 is 1, and then you substitute that there, theta equals 0 means that will be 1. So what's left with this K0 over that? That's equal to 1. From that K0 become this. That's one way of doing it. So if you want to find DC gain, you can also do this way. So you can start with this one. This has to be 1. For that, this should be equal to 1, set to the minus 1. So you will find K0 is equal to exactly same. Now if you can't do this way, just do this method, is fine. So first part done. So second part, we are trying to find H theta. This is same pole repeated twice. So you put K0 over 1 minus B e to the j theta times 1 minus B1 e to the j theta. You can do that. You can do many methods. So we go for H theta squared. We find the modulus of that and the modulus of that and multiply. So the modulus is that, the other modulus is that one. So you got that equation. Now we need to say this is equal to half. See? At theta equal to pi over 4. So you put theta equal to pi over 4 here and make this half. And by cross multiplying, you'll find beta b1. So you go on to the next page. So we found that we put theta equal to pi over 4, it becomes half. That's what is given here. Theta equal to pi over 4, the magnitude squared is half, so half. So you end up with that equation. You now cross multiply, you end up with that equation. And if you simplify that further, you end up with that one. And that's a quadratic equation. You simplify. Now you're going to make this as a quadratic equation, quad, and simplify and find b1. When you look at the b1, b1 becomes 0.32, and then you substitute b1, you get k naught. Now you would have two values for b1. b1 should be plus or minus, because it's a quadratic equation you're going to solve. So you could get a plus and minus answer. Now you're going to go back to the question and see what does it say. It says it's a low pass filter. In a low pass filter case, this has to be positive. Remember we did first order in the class? 1 over 1 minus b1 set to the minus 1 is a low pass filter. b1 is less than 1, greater than 0. And h set equal to 1 over 1 plus b1 set to the minus 1. Still b1 is less than 1 and greater than 0, but this is a high pass filter. Yeah? So you know it's a low pass filter, then you know b1 must be positive. So you need to use that condition to rule out this is not right, only that's the right answer. So that's important. That's how you do that question. Right, the third question is an FIR filter has a transfer function G set, and you've been asked to find out a transfer function FIR filter whose magnitude response is identical to that of G set and has a maximum phase. Maximum phase means all the zeros have to be outside the unit circle. So let's start with this one first. We substitute this one. So that one, when you're writing it, 1 minus 3 over 2 set to the minus 1, and which will be 1 minus 3 over 2z, therefore 2z minus 3 equal to 0, the z is equal to 3 over 2. That's the zeros percent. You can write directly. You can do it from here directly, but this is the way to do if you are unable to do this way. So z equal to 3 over 2. So z equal to 3 over 2 is outside. So there's a 0 there. Okay. Similarly, you do the next one. That will be z is equal to minus 3 over, z is equal to minus 3 over 4. This one will give you that one. So that's inside the unit circle. And this one will give you z is equal to minus 5 over 2. Minus 5 over 2 is here. That's already there. So you know that, and that's all are three given, because they belongs to this one, and then this one, and then this one. Right? What we need to do, maximum phase. So it's important for us to make it maximum phase that this 0 must be reflected outside. If you don't reflect, the maximum response won't be same. So reflect them mean this will become 4 over 3, minus 4 over 3. Now you rewrite the transfer function with this new 0. This one is already there, this is already there. So you don't need to touch that. So you go back and say, right, you are not going to touch this one, so that's exactly the same as that. You are not going to touch this one, that's exactly the same as that, because they're all outside. That's one belongs to that one and that one. But this one you need to change, because that's you are going to reflect it outside. So it is z plus 4 over 3 equal to 0. That's what it is. So you can rewrite that as 1 plus 4 over 3 z to the minus 1. So that's the root. That one. You got that? Now the gain we don't know. So they are exactly same magnitude. So one thing we know would be the gain and theta equals 0 for both one must be same. So you find d theta first. That. Then find p theta first. Then substitute theta equals 0 in both cases. So you substitute theta equals 0 30 times. 30 times 1 minus 3 over 2. Plus 1 plus 4 over 3 plus 1 plus 5 over 2, because these all become 1, right? when theta equals 0, equal to, so that's k equal to, this is what I'm substituting here. Then 30 times, you substitute there, that one, that one, belongs to this. Now you equate them. When you simplify them, your k become 30, so no change on k. So you put 30 there and write to equation, which is this equation, P equation is that. So it's an easy question. It's not very difficult. It just you have to be cautious when you are doing the things. That's all. Next question, obtain a parallel realization for the following set. So we need to do a parallel realization. So this can be split into, you could say A over Z plus BZ plus C over, this is square, so you expand them, Z squared plus Z plus 0.25. Yeah, that's your partial fraction, because parallel means always partial fraction. So this is your transfer function, A over Z, and because this is a second order, you put a first order there, and that's your partial fraction technique. So now you cross multiply, and that fellow here, that fellow there, and you get an equation that's equal to that. Now you equate the coefficients. You have second order value equal to second order, first order equal to constant. So equating the coefficient on both sides, a plus b equal to 1, a plus c equal to that, 0.25, a is equal to 3, right? So here it will come a plus b times of z squared plus a plus 0.25 z plus a plus c z, then plus, then that one 0.25. Yeah, that's your common. Now a plus b is equal to coefficients 1, so that's right. Then a plus c coefficients -4, then that is equal to that. You simplify them, you get your value. So hz become 12 over z, which is 12 z to the -1, and these values are put in, and then you divide everything by z squared, so this will become 1, and rest all in terms of delay. Now you have your transfer function, you need to draw the structure, so that's easy, because this is first part, which is 12 z to the -1, so you start with the xz, go there, 12 times z to the -1, and that output is waiting here. This one is canonic form. Draw a canonic form. First draw the feedback, then feed forward. Feedback is from here, z to the -1, and going in +1 means -1 here, and then +1/4 mean -1/4. That's done. Then here, there's no constant, so that's not there. So -11 z to the -1, -11 z to the -1, because z to the -1 is there. And then -16 z to the -2, z to the -1, -16 z to the -2. Add them, the output here, add them you get. So this is parallel structure, 1 and 2 in parallel. So partial fraction is important. You need to know how to do partial fractions. Next question, a notch filter. You've been given a notch filter, which is that filter. So you've been asked to find the frequency response at DC, and FSO for FS over 2. You know FS over 2 means in our table, that's frequency, that's theta. This is FS over 2, half the sampling, that's corresponds to pi. This is FS over 4, that's corresponds to pi over 2, and that's 0, and that's 0. That's how translation is, right? And this is f equal to 0, this is theta equals 0, theta equals 0 is that position right there. That's that position. So what you do, you just find hz, you have some that equal is like j theta. When you do this one, now first thing is DC, so theta equals 0, h0 is equal to 1 plus 1 or 1, right? It's 2 or 1.81. Or you can substitute here directly. The DC gain is equal to 1 plus this will become 1 when theta equals 0, such the, so 1 divided by, this will become 1 plus 0.81, this also become 1. So it's the same answer you get. You can do it directly or this way as well. Second one is Fs over 4. So that means theta equal to pi over 2. So go back to the same equation that you had here. Substitute at h theta at theta equal to pi over 2. You substitute that in here. When you expand this one as 1 plus cos 2 theta minus j sine 2 theta, and substitute the value pi over 2, and simplify this, you get 0. And the next one is on the next page, but you can see pole 0 position here. These are z squared plus 1, so equal to z squared equal to minus 1, so z is equal to plus or minus j. So you will have a 0 there and there, and the poles are inside the unit circle. So that's 0.8, 0.8. That's sorry, it's not 0.8. It will be square root, and this is square root of 0.8 minus. That's your pole 0 position. Anyway, next part is at theta equal to pi. So go to the next page. You find at theta equal to pi, what's the value? Same thing, you substitute same as what you did before. You get 2 over 1.81. So what's interesting is h theta at theta equal to 0 is also 2 over 1.81. H theta at theta equal to pi also 2 over 1.81. But h theta at theta equal to pi over 2 is 0. So if you plot the maximum response, 1 there, 1 here, 1 there. So it's a perfect notch filter. It's notched the value and comes out. So notching means removing one frequency. That's what it's called, notch filter. So if you have got a 50 hertz and if you want to remove them, you use a filter such that this becomes 50 hertz. So 50 hertz is no longer there in the signal. So it's a notch filter example. Not a design. I haven't done the design of notch filter for you yet, but you should be able to plot, and looking at the maximum response, you should be able to tell what filter it is. Question 7 is you've been given a linear phase sequence, told, and the zeros are at that position and that position, and been told it's a type 2 sequence. So what we need to do is to make sure that for the type 2 sequence you have that. First, let's put that in, that's here, but it must have a conjugate, so it's there. And in the type 2 linear phase, this value should be reciprocal of that. So you should have a 0 there, and that value should be reciprocal, you should have a 0. So by putting that, this is the only one given to you. This is the only one given to you. Now you have introduced this one, and this one. That's how you get the linear phase sequence. The next part, if you look at the type 2 sequence, it must have even symmetry, requires even number of zeros at set equal to 1. So you must put here 0, you must put, because there's already 1 0 there, so you must put another one here. So you've got z equal to z minus 1 is there, you must introduce another z minus 1 because it says even number of zeros. And then it says there must be a 0 at odd number of 0. There must be a odd number of 0 at z equal to minus 1. It doesn't say there must be a 0, there, odd number of zeros. So that means 1 we need to have, at least 1 we should have here. So we must introduce z plus 1 as well. So your transfer function is going to be the original one and its conjugate, then the reflected and the reflected. So there are 4 of those, 1, 2, 3, 4 times. So it will be z minus 1 over 4 e to the j pi over 6. That's the one. And the next one is z minus 1 over 4 e to the power minus j pi over 6. That's the one you introduced. Then the reflected one is z minus 4 e to the j pi over 6 times z minus 4 e to the power minus j pi over 6. They are the complex zeros. Times, already there's 1 there, which is z minus 1, you need to introduce another one because of the even number of zeros at that position. And there's none here, so you should introduce 1, z plus 1. That's your transfer function of this, all the zeros. They only wanted you to find all the zeros, so which we have found out. We can write as a transfer function, or we can leave it as 3 zeros plus these zeros. So that's the answer for that question. And remember, you will be told whether it's a type 1 or type 2. So by reading the type 1 or type 2, you can actually figure out and then get the transfer function. Now here's, just to give you a bit more insight to it, this is a sequence given. They want to know what it is. It is type 1. The reason is type 1 sequence must have even zeros at set minus 1 and set equal to 1. So we got for linear phase that reciprocal of that, so that's done. And you have got 1 on the unit circle, reciprocal of that is 1 over 1 is 1, so that's okay. And then you got here a 0, so that you must have a reciprocal of that. Here's a 0, reciprocal of that, that's fine. But there's no zeros at minus 1, 1, so we don't need to worry, because if present only, they need to have even number. If they're not present, you don't need to worry. So basically, this is a type 1. That's all we have. Identify the sequence type. It's a type 1. Second one is type 2. The reason is, have a look, it must have an odd zeros at set equal to minus 1 and even at set equal to 1 if present. Okay, so we go here, reciprocal of that, reciprocal is there, that one is fine. This one is reciprocal, that's okay. This one is reciprocal. And we've got 1 0 at set equal to minus 1. So, odd number of 0. So that's fine, that satisfies that. And if present, there's nothing here, so we don't need to worry. So it is type 2. Okay. Next one. This is type 3 because it says must have odd number of zeros at set equal, definitely must have minus 1, and odd number zeros at set equal to 1, you must have. So that's type 3. This is reciprocal, that's okay, that's okay. This is reciprocal, this is okay. They got 1 0 here, 1 0 here, therefore it's type 3. Last one is type 4. It says odd number of zeros at set equal to 1. And the number of zeros, if present and set, must be even, if it present. Okay, let's go back here and see. Reciprocal of that, that's fine, that satisfies the linear sequence. There's here one, the reciprocal of that is that, so that's fine. Then you must have odd number at set equal to 1. There's 1 here, that's fine. There's none if present only. There's nothing in set minus 1, so that's fine as well. There's nothing there, so we don't need to worry about that. So therefore this is type 4. So from the poles 0 pattern, you should be able to work out, linearity by reciprocating them, and then you need to work out whether it's type 1, type 2, type 3, type 4. Now we come to question 9. This one is magnitude response and phase response. I've done enough in the class, so start with this one. This is a differentiator, it's a high pass filter. And set transform of that is, I'll go a bit faster here now because you know how to find set transform. Then you find h theta, you get that one. Always you take our half of that out. So half times of that. That will give you a plus here and minus. That will be a sine term. So you need to divide by 2j here and multiply by 2j. Once you do that, you will find this will become, yeah, there I have done it. Then that will become, there will be a j there. J is equal to, sorry. J is equal to e to the power j pi over 2. So it gives you a phase of pi over 2. So this 2 cancel with that 2. This will become sine theta over 2. And e to the minus j theta over 2 times j. J is e to the j pi, so that's that. Now if you add them, that one is it. So your phase is going to be pi over 2 minus theta over 2. Your magnitude response is mod h theta equal to sine theta over 2, that's modulus of that. So sine modulus is basically sine function going from here to pi. Sine is theta or 2. Okay. So this is theta, and this pi should be there, and it's even function. Now remember, at that position, magnitude is 0. So in a phase, at that position, there should be a pi jump. So you basically go and start to put a value there. Substitute at theta equals 0, you get pi over 2. Okay, you put pi over 2 there. And must have a pi jump, definitely, before you draw the negative part. And then if you do theta equal to pi over 2 minus pi over 2 is 0. So they end up here. So that's theta equal to pi, that's there. So that's also 0. So that's the line. And that's the, and you know this is automatically pi over pi. There should be a pi jump at when the magnitude is 0. Okay, that's a very easy one. Next one. Here you've been given 2 samples. You take the first sample and then the delayed 8th sample to subtract them. It's also a type of a differentiator, but a bit harder to understand. So you do the set transform, and that's set for minus 8. So you go h theta equal to 1 minus e to the j theta. You take half of this value out. Remember, I said half of that out. So e to the j theta. This will become plus, that will be minus. Now you divide by 2j and 2j, because whenever you see a minus sign here, it's going to be sine. If it's a plus, you don't need to divide by 2j. You know, it's a cosine. So when you do that, this will become sine 4 theta, which is there. And this j become e to the j pi over 2, that's there. 2 will be there, and e to the minus j is there. That one. So if you combine them, that's your phase part, that's your magnitude part. So phase is pi over 2 minus 4 theta. Magnitude h theta equal to 2 sine 4 theta. We know how 4 theta looks like. So that between pi and that, it will be, that's 0, so it will be there, 1, 2, 3, and that. That's your modulus, and this even function means it will repeat this side. So you can see at that is magnitude 0, magnitude 0, magnitude 0, magnitude, sorry, at that point 0, and then that's 0. We don't need to go there at all, because at pi we stop. Every point at that position, it should, in a phase, there should be a pi jump. Oh, let's start phase. Theta equals 0, we start with pi over 2. There's pi over 2. And it just goes down up to pi by 4. At that point, magnitude is 0. So it must give a pi jump. So that much is pi jump. Because minus pi over 2 pi distance is pi jump. Then it just follows this one. As it must go there, it is 0, so it must jump again. Instead of going further, it can go up to minus pi, but it wouldn't go because of that jump. Then it just continues. And then it sees a 0, then it has to jump again. And then it continues like that, up to that. And then it's an odd function, so you just say it's an odd function. You don't need to spend all the time, you say odd function. And that's sufficient, because you may not have time to draw neatly. Okay? The last question of this one is x minus 4. So set to the 4x minus 4. So set to the minus 4 is just a delay. So it's going to be a general response. It's going to be 1. And modulus of that is 1. So modulus of that is 1. Now the question is phase. Phase theta is equal to minus 4 theta. So you're going to substitute theta equals 0. So theta equals 0 is that. It's a minus. So you go minus 4. And you keep going. You will find at theta equal to pi over 4, it will reach pi. That's the maximum it can go is pi, and then it can't go any further according to our plot. Now if it reaches minus pi, it must do a 2 pi jump. That's a 2 pi jump. And then it's reached plus pi. That's 2 pi jump. We have got nothing to do with 2 pi jump, it's nothing to do with the magnitude response. Pi jump is just, there's no zeros here. The magnitude never goes to 0 here, it's all flat. Now it goes and it's in parallel, comes there again at some point it's pi, and just jump again and then goes down. So and this may not be exactly pi, it may not be 0 at pi, so it could be there at that position. So that's how you draw, and then just say it's an odd function. That's fine. So I've given you an example to show where you get pi jump when the magnitude response shows a 0, and where you get 2 pi jump when the phase goes up to minus pi or plus pi. You can't go any further. It has got to jump upwards or downwards, depends. This question wasn't in your tutorial problem sheet, so we have now added this one. Basically, this question is, you've been given a block diagram. That's a block diagram, and we want the impulse response. When you give an impulse, we want the output is going to be a cosine function. It's like a cosine oscillator. It's like that. That's what we want. So it's a cosine oscillator that we are interested in this. And in order for that to happen, what are these values should be in order to get that happen? So it's a basic digital oscillator question. And digital oscillator question, we have learned that yesterday. The second order, the B2 and B1 stability triangle tells you that for an oscillator, B2 should be equal to 1. That we know. Or in terms of pole 0, the poles must be on the unit circle for an oscillator, marginally stable, we call it. That is R equal to 1, that is B2 is equal to 1 as well, the same thing. We need to know that. So basically you could simply say this should be equal to 1. Very easily you can do that. But let's move on and how we do this one. So go to the next page. So I have, this is my structure. This is what I want. So what I did is I took the set transform of that from the set transform table. I got that equation. I know that set transform table tells me that's my equation. That belongs to a second order system. So what I do is then is I write the transfer function of this first. The transfer function of that, very easy, you know, y over x is equal to a naught, a1, a2 added up, divided by 1 plus b1 plus b2. Now, when I give the x as delta, I must get this. That means these two transfer functions must be same. They are identical. If they are identical, so rather than equal, you could say identical. What does that mean? A naught must, coefficient A naught must be equal to that multiplied by that A. So that's done. A1 should be equal to A times of cos theta naught minus cos theta naught. So A1 is that. A2, there's no A2 here, so it should be 0. Then B1 is equal to minus 2 cos theta naught. And B2 is equal to 1. And we know that B2, 1, we set them earlier. So these are the conditions that you must have in order to have this system oscillating and also giving you a cosine waveform. So this is kind of a different twist in the question. By giving a structure, find all these values. Earlier when we did in the class, we didn't have any of these at all. We set up initial condition to oscillate, or we gave an impulse. In this way, if we move them around slightly and introduce that section, that part as well. So you don't need to worry about initial condition. As soon as you give a small impulse, it will give you a cosine waveform output. That's all I think that's all this is the last question. So I've covered everything for chapter 5. So you should be able to look at this question and look at other questions in the chapter as well. Should be able to do them. Okay.